First, an basic introduction on the difference between a normal reinforced cement concrete beam as well as a deep beam. We can see a figure here. Figure 1 is having a long beam where the length of the beam is very high on comparison with the depth of the beam. So this beam, upon the action of the load, will behave in pure flexure, and all the theories of the simple bending is applicable for the normal or the or this beam. The second figure is a deep beam. Deep means the beam having very large depth on comparison with the length of the specimen. So even both these are termed as the beams, the behavior of these beams on the action of the loads are different, which is important for the design purposes. So on comparison with the long beam, the deep beam will be very strong in flexure. That means this beam won't bend at all, and the possible failure is only by the shear. You can see some applications where the deep beams are used. Here on this left hand side, I have a arrangement of beams and columns. You can see the deep beams are used as the transfer beam for transferring the heavier load from this top portion to the columns. So this beam is a deep beam. And one more advantage of providing deep beam at this location is that we will get enough clear large open spaces here. Suppose this was continuing, we don't have the openings here, and if you want to use for parking and all, it won't be possible. So this deep beam will help in that way. This is a real picture showing the position of the deep beam. The deep beams are also used in the case of bridges. You can see the girders, the topmost portions are supported on the pier, and the load on the girder is transferred to the pier through the deep beams. So the behavior of deep beam is very different from the normal beam. So that's a important thing, and the design is also focused on the behavior of these types of beams. Before going into the next slide, I'll just show you the IS code. So this is IS 456-2000, and so we already studied the design of concrete structures 1 and 2 courses, and when you see through the contents, the first one is general. Then in section 2 there are different details about the materials, workmanship, inspection and testing, and the third section is basically on the general design consideration. Under this section, you studied the design of beams, columns, then the minimum cover for prevention from the fire, and other basic structural elements. The section 4 is entirely devoted to the special design requirements for the structural members and systems. So this will be our focus, especially in the first module. In the section 4, you can see in the IS code there are concrete. I'll just maximize. So 28 is on the concrete corbel, the design procedure, and 29 is on the deep beam. Then 30 is on the rib slab, and you can see also 31 is on the flat slab, which will come in the module number 2. And walls, it's not there in the syllabus. The stairs and footings you already learned in the design of concrete structures too. Okay, so when I search in the PDF deep beams, you can see like there is some definition for the effective depth. This is not applicable for the deep beams. So always in the code, the deep beams design are treated separately. You can see these deep beams comes under the special member category. Yeah. So this is the section 4, and these are the corresponding guidelines or the caudal provisions for the design of concrete corbel. Section number 28 close, and 29 is on the DP. So these guidelines or these clauses will act as the basic skeleton or the basic framework for designing the corresponding structural elements. So we can see the uh, close DP. There are some general definitions on how it is defined, and the lever arm conditions, and the minimum reinforcement in positive reinforcement, that is sagging reinforcement, and the minimum negative reinforcements that has to be provided for deep beams. And also there are vertical reinforcement conditions and the side reinforcement condition. So coming back to the PPT, for a normal beam, say it's fixed at both the supports, when it is loaded, it will have a normal bending where the bottom portion will be sagging, and over the supports it will be hogging. You can see on the failure of this beam, there are various types of cracks, which ranges from the flexural cracks, as it is forming above the supports, it is a negative. For negative moment, they have flexural cracks, and there will be a shear cracks, which will be always inclined to the uh, lengthwise direction of the beam. That's why we are providing the vertical stirrups, and there will be flexural cracks at the midpoint or the midspan, and there also may be some combination of the flexural and the shear cracks, depends on the length and the design of the beams. So when you see when you strictly closely when you have a close look on these cracks, you can see that the flexural cracks are always normal to the length direction of the beam, and the shear cracks are always inclined. So this corresponds to the uh, normal uh, beam, reinforced beams, and these beams will obey the simple bending theory. On the right hand side, I had placed the figure of a deep beam. So you can see that the length of the beam is very less on compared to the depth of the beam. So this makes, as I told, very these beams very resistant to the bending, and the behavior on the action of the loads will be very different from the normal beam. So here comes the strut and tie uh, philosophy, where when on the action of the loads on the beam, there will be some formation of, you can see I'm drawing on the figure, the compression studs. This will be the compression studs, and the bottom will be the tension studs. So the entire behavior of the deep beam can be idealized into the strut and tie action, in which the total beam you're converting to a truss action, like where there will be a combination of compression studs C, and tension studs. So what are these? Strut and tie, the important philosophy for designing the deep beams. The strut and tie modeling STM is a simple method which effectively expresses complex stress patterns as triangulated models. So you are dividing or you are idealizing the complex stress patterns which may occurring in the deep beam into very simple truss-like models. And this STM is based on the truss analogy and can be applied to many elements of concrete structures. So same philosophy will be using for the corbels also. It is usually adopted to design non-standard elements or part of elements of concrete structures such as pile cap, corbel, which will be the next section, deep beams, and also can be used for sections like for the beam with holes and the connections, where the normal beam theory does not necessarily apply. So this will be our basic philosophy for designing the deep beams. So you can see this will be the compression struts and this will be the tension struts. So how to classify the deep beam and how to define the deep beam. So in the right hand side I have placed the caudal provisions. I'll directly go to the code. Yeah. So in the section 4, the clause number 29, deep beam. By definition, a beam shall be deemed to a deep beam when the ratio of effective span to the overall depth L by D is less than 2 for simply supported beam and 2.5 for continuous beam. So if the length effective span to the overall depth L by D value is less than 2, that means uh, that the for simply supported condition, if it is less than 2, it is a deep beam, and for continuous beam for less than 2.5, it is a deep beam. So these are the basic definitions or how we are defining the deep beam. And there are some provisions for finding the lever arm for the calculations. There are different equations for simply supported beams as well as for the continuous beams. So even in the simply supported beam, there are two equations for the lever arm, which is based on the value of L by D ratio. If it is between 1 and 2, we have one equation, and for values less than 1, you have another lever arm equation. The same is applicable for the continuous beams. You have two sets of equations. In these equations, L is the effective span taken as the center to center distance between the supports, or 1.15 times the clear span, whichever is smaller, and D is the overall depth. And we have just seen that there are some conditions or provisions for placing the reinforcement, where to place the reinforcement in the beam depth, as well as what should be the minimum quantity of reinforcement. So coming back to the PPT, so the right hand side is the uh, clauses we have discussed from directly from the code. So we learned how to define or the how to classify the deep beam. It is for L by D less than 2. For simple supported, it is a deep beam, as well as if the L by D is less than 2.5 for continuous beam, the same is a deep beam. The clauses I have just placed here. So I think you have the code with you, and we will see a problem so that the clauses will be thorough with you. So in the question, it is to design a deep beam Design a simply supported beam of 4 equal span. Effective depth is equal to design a deep beam. To design a simply supported beam of 4 equal span, the effective depth is equal to 1.6 meter. The clear span is given as 2.4 meter, and the beam is subjected to an UDL of 30 kilonewton per meter. Design and sketch the beam with detailing. This is the question. So the basic inputs, uh, we have to use the M20 concrete, FV 500 steel. The breadth of the beam is 300 mm or zero point 0.3 mm, zero point 0.3 meter, and we have given the depth. Effective depth is equal to 1.6 meter. The clear span is 2.4 meter, and UDL is also given 30 kilometer meter per meter. So the first step is to find the overall depth for classifying the deep beam, or classifying or check whether the given beam is a deep beam. So by providing a effective cover, d dash is equal to 50 mm, we can find the overall depth as total capital D is equal to the effective depth small d plus effective cover d dash is equal to 1600 mm plus 50 mm is equal to 1650 mm. So this will be our overall depth. Step 2 is to find the effective span. So we have just seen how to find the effective span. Should be either of the distance from the distance between the center of supports, or 1.15 times the clear span. So we're directly taking as 1.15 into clear span here, as we are not provided with the center to center distance between the supports. So by adopting the equation, 1.15 into clear span will give you 2.76 meter. So we know the total depth of the beam. We know, or we calculated the effective span. So by L by D ratio, we will get L effective by D is equal to 2.76 divided by 1.650, which will give you 1.67. Okay, so coming back to the closest, you can see on the right hand side for L by D ratio, if it's the case of simply supported beam, up to 2, less than 2 means it is a deep beam. And you can see this was the provisions for finding the effective span. uh, just in the cursor you can see here. Okay, so we found the L by D value and found to be less than 2 simply supported beam. So this parameter is satisfying with the deep beam condition. So we have to design this beam as the deep beam. The corresponding caudal clauses are listed here. And the next step is to find the lever arm. So we just mentioned that for simply supported beam, there are two lever arm values for different conditions. Our L by D value is sorry, value is 1.67, which is in between 1 and 2. So we are supposed to use value Z is equal to zero point 0.2 into L plus 2D. So by using the equation, Z is equal to zero point 0.2 into L effective plus 2D is equal to zero point 0.2 into L effective. We know 2.76 plus 2 into 1.650, the effective depth, which will give you the lever arm as 1.212 meter. And next is the calculation for the loads, which we have already done for designing the normal beams is given UDL 30 kN per meter. We are factoring it 1.5 times 1.5 into 30, 45 kN per meter will be the factored live load. Dead load calculation, we know the section of the beam. So by factoring it with 1.5, 1.5 into 1 into zero point 0.3 is the breadth of the beam, into 1.65 is the depth of the beam, 25 is the density of the RCC, which will give you the self weight of the beam as 18.5625 kN per meter. So by adding the external load plus the dead load of the beam will give you 65 kN per meter. So we establish the loads. Then the step 6 is for finding the design moment. We know simply supported with the UDL load. So we know the bending moment equation, and the bending moment is equal to W L square by 8 load into, yeah, 2 point clear span. Okay, so W is a load, into L is the clear span 2.4, square by 8 will give you 46.8 kN per meter floater meter as the design moment. So the calculations for the positive reinforcement area is in the step 7. We know the equation AST is equal to ultimate moment divided by sigma st into Z. The lever arm will give you the AST. So the moment value into 10 power 6 kilometer meter by converting to Newton mm, and divided by 0.87 into 500, because you're using the FE 500 steel into lever arm. This is 1.212 into the conversions is again given here. Sigma st is equal to 0.87 into F by Z is equal to 1.212 into 10 power 3. Okay, so by using these equations, we will get the AST as 88.767 mm square. So this is a calculation, and we want to check whether we have provided the minimum reinforcement. The percentage of steel is given by AST by BD into 100. So we have provided 88.767. The divided by the cross sectional area into 100 will give you 0.0184 percentage. We have to provide a minimum of 0.3 percentage. That will give you, applying the minimum reinforcement to the section, will give you the minimum quantity of steel as revised one as 1440 mm square AST is required. And you can find the number of bars. Total area divided by pi d square by 4 will give you the number of bars required for the posterior reinforcement. So now we calculated the required posterior reinforcement. Now there are some, these step 10 and step 11 is based on the caudal provisions. The step 10, embedment of reinforcement beyond the base. Yeah. So in the uh, slide, you can see 29.3 reinforcement, 29.3.1 posterior reinforcement. The tensile, I'll read out the clause. The tensile reinforcement required to resist the positive bending moment in any span of a deep beam shall extend without curtailment between the supports. That means, uh, suppose this is the deep beam. And normally we'll be providing the suppose you have a supports here. The first A means that extend the reinforcement without curtailment between the support. So this is between support from here to here. On the clear span, there should be the full length of reinforcement that is stated in the A. Then second one, it should be embedded beyond the face of the each support, so that at the face of the support it shall have a development length not less than zero point 0.8 into LE, where LD is the development length. You learned this equation for finding development length in your previous classes. And for design stress in the reinforcement, and so this is regarding the requirement of the reinforcement. The C is on the placing, where to place. It should be placed. That is, at what depth this reinforcement should be placed. Be placed within a zone of depth equal to 0.25D to 0.05 L adjacent to the tension phase of the beam, where D is the overall depth and L is the effective span. So for this D beam, this will be under compression and this will be under tension. That means top will be compression, top bottom tension. So from the tension region, from the tension phase, for this distance 0.25D to 0.05 L should be the position of the reinforcement. So we know the development length to be provided, and we know the place where the reinforcement has to be provided. So corresponding calculations are coming in the step 10 for finding the development length, and step 11 is for finding the placement. Okay, so we know beyond the supports, the rebar should be extended for zero point 0.8 into LD. For those who are not clear why there is a requirement for the development length, see, if you are curtailing the reinforcement at the support point, suppose you are, I'm just putting a dot here, or I'm putting into. So suppose you are stopping the reinforcement at the face of the supports, there in a simple way there won't be enough grip for the reinforcement. For providing the enough grip for the reinforcement or for the development of the stress, we are giving an development length. I'm just giving an enlarged way. The same reinforcement is extended here. So that's the requirement for the development length. So zero point 0.8 into LD is the value. We know the LD value is given in the IS code and the corresponding clause for finding the development length. So zero point 0.8 into 5 into sigma st by 4 tau bd. Tau bd you can find from the IS 456 2000 page number 43, which you already used for the basic design. So I'm not again showing those clauses. So by substituting the values, we will get that minimum of 544 mm should be there as the developer length. So that means this length beyond the support phase, there should be 544. Okay, so this should be the length of the developer length. That is in the step number 10. And the step number 11 is for finding the zone of placement. So 0.25D minus 0.05 into LFT. So calculations 0.25 into 1.6. Sorry, it's like the minus. So 0.25 into 1.65 minus 0.05 into 2.76. That will give you a value of 275 mm. So the tension reinforcement, this reinforcement has to be placed 275 mm from the bottom face. Okay, so this length should be, or this height should be 275 mm. So we calculated the position of the reinforcement. Then there are two more clauses for step 12 for finding the vertical reinforcement, as well as for finding the horizontal reinforcement. Again, back to the code. One more thing to note that there is no requirement for the negative reinforcement, as this is simply supported beam. If it was a continuous beam where there will be hogging moments at the supports, we have to provide the reinforcement according to the close 29.3.2. So for this problem we are just skipping the 29.3.2. This is also very similar to the posture reinforcement. The first portion is regarding the termination of the reinforcement, and the B is on the location of distribution of the reinforcement. So you can go through these clauses if the question was asked for a continuous beam. And the clause number 29.3.3 vertical reinforcement, and the 29.3.4 is on the side face reinforcement. So that means that if the force are applied to a deep beam in such a way that hanging action is required, bars or suspension stirrups shall be provided to carry all the forces concerned. And regarding 29.3.4, side face reinforcement, the side face reinforcement shall comply with the requirements for the minimum reinforcement for the wall. So this is straightly uh, focusing or straightly linked with the minimum reinforcement for the walls, and there are some uh, guidelines for the vertical reinforcement also. So coming back, the regarding the vertical reinforcement, but the vertical reinforcement will be the stirrup reinforcement like this. We are providing the uh, vertical reinforcement in a direction perpendicular to the length of the beam, and the value will be 0.12 by 100 into B into D. That is, as they are using the Fe500 HYST bar, the reinforcement is 0.12 percentage, and if it was a mild steel, it was 0.15 percentage. So the ASTB is equal to 0.12 by 100, 0.12 percentage of the cross sectional area, 0.12 by 100 into 300 into 1000. So that will give you. So we are defining for a 1 meter length will give you 360 square as the ASTB, and by knowing the area of reinforcement we can find the corresponding spacing after choosing the diameter of the stirrup bar. So we are providing the 8 diameter bars, and from this area as well as the provided diameter bars we can find the spacing required for the vertical reinforcement. And so we have provided the spacing, and there are some clauses regarding the spacing of vertical reinforcement which are already laid the minimum spacing. It is checked with those conditions. And the other thing, uh, the side face reinforcement 29.3.4, side face reinforcement shall comply with the requirements of the minimum reinforcement of the walls. See 32.4. We will just so the 32.4. Yeah. So the uh, 32.4 is on the design for horizontal shear, critical section for shear, nominal shear stress, and 32.41, 32.4.2.1. Okay, so based on these reinforcements guidelines, uh, the minimum reinforcement required for the slabs, for the bolts is given by ASTH horizontal reinforcement is equal to 0.2 percentage of the cross-sectional area. Will give you zero point 0.2 by 100 into 300 into 1000, will give you a value of 600 mm square. By knowing the area and by providing the 8 diameter bars, we can find the spacing required for the horizontal reinforcement. And the we already discussed that the deep beams are strong in flexure, and they have to be checked for the shear also. So the shear value we are checking that the normal shear check Bu is equal to total load W into L divided by 2 will give you the shear force. We can find the shear stress by tau B is equal to Vu by Bd by the cross sectional area. B into D will give you 0.1625 Newton per mm square, which will give you a tau C value is equal to 1.1 the tau C value is 1.11 Newton per mm square. So as the tau B, that is shear stress, actual is less than the allowable shear stress of 1.11, this design is uh, safe for the shear. So the last portion of this problem is on the detailing. So we have found the posterior reinforcements required for taking the moment. We found the location where the same has to be placed. We found the minimum vertical reinforcement required as well as the horizontal reinforcement. Now it's time for uh, do the detailing. So you can see here the deep beam detailing. The clear span is 2.4 meter. That is from the face of the support to face of the right support. It is 2.4 meter, and this green line shows the positive reinforcement. And from here, just see my mouse pointer, from here to the left of this point is the development length, which is given as LD is equal to 544 mm as per the caudal provisions. And these red lines these red lines are the uh, horizontal as well as the vertical reinforcements. So a closer look in the cross section of the beam shows the reinforcements in a very clear way. You can see that the depth of the beam is 1.6 meter, the total depth, and D is the effective depth is 1.60 meter, and this was the effective depth we have provided 50 mm. The breadth of the beam is 300 mm. So the other this green line are the posterior reinforcements, and we have provided the 8 mm dia stirrups as we designed here. 8 mm diameter stirrups, and also the AST the AST V 8 mm diameter bar and the AST H horizontal rebars you can see as the dots here in this cross section. They are also 8 mm. Sorry, they are also 8 mm diameter bars of 160 mm center to center spacing. So the detailing or the arrangement of the reinforcements are shown in this way after the design calculations. And yeah, this is this is regarding the design of a deep beam, especially for a simply supported case and for the UDL loading. So I will stop for today, and I will take the class at 11:30 tomorrow. That is a free slot for you for both A and B patches. So we will meet tomorrow at 11:30 a.m. for the next class. Thank you.